So in the past few lectures, actually in the past two lectures on mathematical methods, we have devoted those to vector spaces. And so we have developed the concept of vectors, or we could say that we have developed vectors. But with that, a question arises, and of course that is, what can I do with them? So first and foremost, we can transform vectors, right? So transform vectors. And we are going to devote a great deal of attention to this topic of transformation of vectors, right? But now we cannot transform them in any arbitrary way, right? Because if we were to do that, then it is a possibility that we might break some of the defining properties of vectors that we have developed in vector spaces, right? So then we have to define a linear transformation, right? And so now we're going to talk about linear transformation, or a linear operator that will transform a vector, right? So a linear transformation on a vector space, say V, it assigns a vector x or y that belongs to this vector space V, the vectors ax and ay, such that for some scalars that are a and b, we have a, which is the transformation on ax plus say by, right? And that gives you ax plus bay. Now note over here that these x and y are the vectors that belong to this vector space V, and these a and b, they are scalars, right? And that's why we can write it like this. Well, the other one is, the other feature you could say is that the product of two a and b, that is a and b transformations, is defined by a bx, which is equal to a times bx, right? That is just a new vector for a to act on, right? Okay, and so finally the last one is that the sum a plus b on x, b, is equal to a on x plus b on x, right? Okay, so from here let's actually talk about some examples, right? We'll look at some examples. So examples, right, of what we have just defined above. So for some field Fn, now if you remember from vector spaces, this is simply a space of n tuples, right? Well, then the matrix multiplication mv with square matrices, square matrices that are n cross n, right? It works, right? And we already know that from experience that a matrix M on a x plus by is a, where again these small a and small b are scalars, right? So it's a mx, so the matrix acts on x vector and it acts on y vector. And that is for all x, y that belongs to this space of n tuple, right? Now, second one, where we could talk about, say, polynomials, right? So we will consider Pn polynomials, that is polynomials up to some degree n, and we will consider the operator dk, which is simply the derivative operator, that is dk over dtk, right? Okay, so with this now we can consider dk acting on a polynomial or acting on this thing, that is ax plus by, right? And what well, if you use this definition for dk, that simply becomes dk over dtk of ax plus by, right? And with this then you can distribute this in both of these, and what you would have is then a, but that's a scalar, so that comes outside of the operation, and you are left with dkx over dtx plus b times dky over dt k. I'm sorry, I wrote over here x, it was dtk, right? And this thing is then simply a xk plus b yk, right? Okay, so well, over here this xk and this yk, let me just write it like this, xk and yk, they also belong to this Pn, right? Okay, now note over here that the way we define this differential, right? We this differential operator as dk as dk over dtk. But can we define an operator for integration as well? Maybe say I, right, acting on x, that is something like integral of x dt. Is this thing possible? Well, it actually is not possible. It does not work. And the simple or the simplest reason for this is that for some Pn, right, I have this, say I take this integration and I apply it on some power Tn, right? What is that? What does that do? That in general, integration increases power with 1. And so what happened with this thing is that it is not anymore the member, or it does not belong to this set Pn, right? It instead, of course, it belongs to some Pn plus 1, but it does not belong to this space, right? And therefore we cannot do this thing, right? So this thing is not going to work, right? Okay, and we are going to look at this in a bit more depth somewhere later on in this video, right? Okay, so from here now, there are two special linear transformations, and those are 0 on x, it gives you 0, so it gives you null, right? And the other one is the identity on x gives you back your x, right? So you could think of this as 1 multiplied by some vector x is giving you back that vector, right? Or in terms of number, 1 times 2 is just 2, right? Of course, I don't have to go into that depth because I'm pretty sure you already know about this. So over here, the exact form of these, they depend on the form of the vectors, right? Okay, now we could also talk about the product of transformations, and they actually, let me just write this down, product of transformations. Well, the product of transformations enjoys a host of properties, right? So that's just a number of properties, and we could list them down. They are, say, first one, of course, in no particular order. A0 just means same thing as 0 on A, or 0 composition A, and that gives you back 0, right? And the other one is A times identity. Now you could write identity as this thing or as this thing, right? E. So I'm going to use E for identity. Okay, so this thing is the same as identity first and then the matrix A, and it means the same thing as it will give you back A, right? That's what the identity does. Now C, or the third property we could list, is A times B plus C is the same as A times B plus A times C. And moving forward, we could have two more actually. So let me write one of those two. A times B times C in brackets, right, is the same thing as if I were to do first A times B and then act it on some C. And the last one is some scalar A acts on A is the same as if A acts on A, right? So this thing and this thing, they are the same, where of course this small a is a member of or belongs to the n tuple F, right? Or to the field, right, F. Over here, I did not talk about one of the property, and that is because, well, the property is, or it could have been, that A times B is equal to B times C. But this thing is, it's not guaranteed, right? It's not always true. Well, of course, by now you should know that if it is true, then we say that we have an abelian set, or or a abelian group. If it's not true, then it's simply non-abelian group, right? Okay, let's move on from all of this and go further and talk about inverses now, right? Okay, so we're going to talk about inverses, and so far vectors, we know that for vectors, we know that for any x that belongs to the vector space V, there exists some x inverse, right, that also belongs to V. We talked about this in vector spaces, right? And this is such that if I were to have x plus x inverse, right, it should give me 0. Or in general, we could say that x composition x inverse gives me identity. It just happens to be that the identity for this plus operation is 0, right? Okay, so the question over here now is this, we know this for vectors, right? This thing is for vectors. The question is, what about linear transformations, right? Do they as well have an inverse? And if so, then is it additive or multiplicative, right? That's the question. So we are going to focus on this question and we will try to answer that. So let me move on to next page, right? So first of all, if we consider a vector space V, then the set of all the linear transformations, right? All the linear transformations that act on this vector space V, they as well form a vector space itself. So what I mean by that is that it forms this set that is A, B, and other elements. They belong to some vector space V prime, right? So these are these A, B, and so on, right? They're the linear transformations, and they themselves make a group which belongs to this vector space V prime, right? Some other V, right? Okay. So such that it satisfies, so it has to satisfy some of the properties, and let's talk about those now. The first one is that there exists an operation, so let's call that plus, right? There exists an operation plus such that this set of V prime and this operation plus forms an abelian group. So it forms abelian group, of course, with the identity being 0. Right? Okay. And the other property would be that it has to satisfy, that this thing has to satisfy is let me draw this circle for this first one, and we will talk about the second one over here. And it is that yeah, for every alpha that belongs to the field F, there exists a transformation alpha on A, alpha times A, that belongs to some vector space V prime, right? So this one, right? Okay. Yeah. And there are some properties for this. Let's start with A. That is that alpha times BA is the same as alpha times B, which acts on A, right? The other one is alpha times A plus B, which is equal to alpha times A plus alpha times B. And let's see if I can write these, squeeze them here. So the third one is simply identity on A is equal to A, right? So it gives you back A. And that is true for all A that belong to the vector space V prime, right? And the last one is if I have this some alpha plus beta, right? So these are now two different scalars on A is the same thing as alpha A plus beta A, right? Okay. So with this then, I have answered part of the question that, I have answered the question that yes, right? The linear transformations have an inverse, and for now we have talked about the additive inverse. So yes, there always exists an additive inverse to any linear transformation. That is, I could write it as A plus A inverse, and I'll use this plus symbol over here in the subscript to show that this is the additive inverse, and that should give me 0, right? Okay, so well then what about the multiplicative inverse or the product, right? That is A composition, or A times A inverse is identity, right? Does this thing A inverse, does this even exist in the first place? Okay, so well, to actually answer that, this notation that I defined over here, let's clean that up a bit. Since, well, we know already now that the additive inverse is simply the negative of the matrix, right, or this A, right, the transformation. That's true for the additive part. And so if that's true, then we can simply go ahead and call this one for the product, right? And this is for composition, that is what I'm defining as the product. So the product inverse can simply then be denoted as A inverse, right? So if I'm using this thing, that is just showing you that it's the inverse of the additive inverse, and this one is telling you that it's the multiplicative inverse, right? Okay, so with that out of the way, here we go. If a linear transformation A has both the following properties that I'm going to list now, in that case A inverse will exist. So A inverse exists when first one, let's label it as A, and the first property is if x is not equal to y, that would imply that the vectors that these x and y make, they are also not equal, right? Or if x I used equal here, I meant if x is not equal to y over here, then the vectors that they form will also not be equal, right? And the other one, the other case for this same part A could be that if A, let me get rid of this x, yeah, if A x is equal to ay, right, that would simply imply that x and y are same, right? Okay, so then let's talk about the other property that has to be true, and which would imply that this A inverse exists, and that is that for every y that belongs to the vector space V, there exists x that belongs to some vector space U, such that A x, when this transformation acts on some vector x, it gives you vector y back. Now, if you did not understand this so well, it's okay, because I'm going to give you some examples which will clear all of this up. We'll use this part A of the definition, and we'll also use part B of the definition for the definition for an A inverse, the existence of the inverse, right? So for that, let's go ahead and consider the transformation, that is the rotation one, and that is, okay, so I'm going to use some funny notation where for sine and cosines. I have already mentioned this in previous videos of mine, but I don't know if you remembered it, but I use this theta under this gamma with this line, this as cosine theta, and this sigma, theta under a sigma is my sine theta, right? What this does for me, it helps me to it is just because I'm lazy, right? And so of course what it does for me is then I don't have to write all of these C, O, S and theta and all that things, right? Okay, so I'm going to put this over here. I'm not going to get rid of it, so you can come back and look at this. So yeah, so the rotation is in R2, right? In R2 is written as cosine theta, right, minus sine theta, and sine theta cosine theta, right? And this will of course act on R2. So now let's talk about this property, right? This property, or the part A, right, of this definition. So for that, we will take some, let me just write down A over there. This A is corresponding to this A, right? So that part of the definition, right? So for this, let's take some X, which is A, B, and let's pick some Y, which is C, D, right? Okay, so in this case, if I were to act with this r theta on X, what will I get? If you do the math, right, this is your r theta, and here we have defined our X and Y's, right, in this thing. So you take your matrix r theta and you act it on this vector X, that is, you just take the product, you end up with A cosine theta minus B sine theta, and in your second row you have A sine theta plus B cosine theta, right? Yeah. So if this is the result that you would get if I were to take this rotation operator and act it on X, and let's say if I were to do the same thing with Y, what do I get? I'll get C times cosine theta minus D times sine theta, C times sine theta plus D times cosine theta, right? Okay, now we will use from this A, we will use this one, right? This is what we will use. And so if we use that, what then we have to do is, should I continue over this side? No, I'll not have space, of course. I'll go down over here, right? So see, I'm going to use this one, right? And so what that means is then I have to equate for my rotation operator, I'll have to equate r theta on X is equal to r theta on Y, right, from this thing. So let's go ahead and do that. So if we do that, r theta on X is equal to r theta on Y. What does that imply? That simply tells you that A times cosine theta minus B times sine theta is equal to C times cosine theta minus D times sine theta, right? And the other equation you would get, or the other expression would be A times sine theta plus B times cosine theta, which is equal to C times sine theta plus D times cosine theta, right? Now if I were to collect some like terms together, right, and factor them out, what do I get is A minus C from this first expression. See, you have A with cosine theta and you have C with cosine theta. So I'm just factoring those out. So A minus C times cosine theta is equal to B minus D times sine of theta, right? And from this one, what would I get is, I have, with sine theta, I have A and C. So again, A minus C, this time with sine of theta, is equal to minus D minus B times cosine of theta. Now if you look at these two set of equations, they go ahead and they imply that that your cotangent theta has to be equal to minus tangent theta. But of course we know that this thing over here is never true, right? It's never true. And with this, then it simply implies, or this thing tells you, that your A has to be equal to C, and or your B has to be equal to D from this two set of equations, right? Because that's simply because this thing is not true. It's never true, right? And so therefore we have, let me go up here. Yeah, we have talked about this part A, right? This one. Now let's talk about part B of this definition. And that one is very simple. It does not really require a lot of mathematics, but let's do the part B of that definition. We could consider some y, that is a, b, and if we do that, then x is simply a times cosine theta plus b times sine theta, right? And minus a times sine theta plus b times cosine theta. Now this thing is such that your r theta of on x gives you y, right? And so if I were to take this operator, rotation operator, where did I define it? Yes, this one over here, and act it on this x, so I should get this y back. And so you can take this x that I just wrote over here and apply the rotation operator and see, check if you get this y back, right? Do that as an exercise of your own. We got this, of course, from the fact that we already know that R inverse is simply cosine theta sine theta minus sine theta and cosine theta, right? Okay, so well, this was very nice and simple. Let's consider a less fortunate example, right? And here we will talk about this d on the n degree polynomial, right? So let me actually write it. How about if we were to act with d on some n degree polynomial, right? That's the question. So if we go back on this definition for the existence of an inverse that we talked about in this place over here, we are again going to take this part A and part B and look at those separately. So let's do for part A first, right? So yeah, let's go down. Okay, now for part A, let's take some x, which is t squared plus 2, and some y, which is, let's say, t squared plus 3, right? Now with this, then if I were to take this dx, right, which is simply take the derivative of this function with respect to t, what is that? Of course you should know this, it's simply 2t, right? And if I were to take the same thing for dy, that is 2t. And so in this case dx is same as dy, right? And so this then we could say that x is equal to no, 1 minute. Yeah, we could say that this dx and dy are same. So if you go back on this property over here, right, so we could say that x and y are the same. Okay, now let's talk about part B, right, of our definition. So for this we could take for some y, that is Tn plus some other terms, right, there exists no x, right? So there exists no x that such that if I were to do this dx, I could get back y, right? And over here, I think I missed this. This thing is true, right? Of course, that's true. But if you go back over here, yeah, look at this definition, right? This thing in this case for a derivative, dx is equal to dy. We just checked that. But this here says that it implies that x is equal to y, right? But if you go down and you look at this, the function that we chose, it was this, x was t squared plus 2 and y was t squared plus 3. But of course they are not equal, so x is not equal to y. And we just, for this part B, we also saw, wait, what happened? Yeah, for part B also, we just saw with this that there is no x, right? Such that if I were to take the derivative of that x, I would get back this polynomial, right? What does this imply? This implies that this d on an n degree polynomial has no inverse, right? And so that's why when I started talking about this, I said, let's consider an unfortunate example, right? Okay, now, yeah, what we just talked about, these are of course the characteristics of one-to-one and on-to, or you could say injective and surjective, right? We could so we could dig a bit deeper and we could consider yeah, we could consider that, say, if ax is equal to 0, what does that imply? That implies that x has to be 0, right? And if this is the case, then we can say that a is invertible, right? And I just gave this statement out of the blue, right? But what we can do is we can prove this, and to do so, just start with the first part of the definition, right, for the existence of the inverses. That was ax is equal to ay, right? If this is true, then x has to be equal to y, and then a is invertible, right? That was the case, right? That if this happens, then a is invertible. Then this thing ax minus ay is equal to 0, right? Which is the same as, if I use this linearity of a, I can write this as a times x minus y, right? But if a is invertible, right, which we just said from this thing, if that's true, then this simply means that x minus y has to be 0. And so if x minus y is 0, what does that imply? That implies that x is equal to y. And so this thing is then satisfied, right? And so then we can go ahead and state this thing, that ax is 0, which implies x is 0. And so if that is true, then a is invertible. Okay, right. Now, for finite dimensional vector spaces, it turns out that either part A of our definition or this theorem that I just proved, this one, right, that it's also, you could say, injectivity it is sufficient to determine if A is invertible, right? And this is because A maps X, right, that belongs to some vector space U. It maps this thing, let me just, yeah, to some Y that belongs to vector space V. And the only way that it isn't surjective is if it is a degenerate map. So let's consider over here. First, let's talk about this function that takes V and maps it to V prime. That would look something like, yeah, you have these points. Let's say this one is V1, V2, V3, right? And this, it maps, the function f maps it to V1 prime, V2 prime, V3 prime, and we have some V4 prime. But this f takes it and it maps V1 to V1 prime, V2 to V2 prime, and V3 to V3 prime. And f is the map, right? And we could also consider this one where f takes V to some U, where this V, or let's, yeah, here we have this V1, V2, and V3, right? And in this U, we have U1, U2, U3. And so V1 maps to U1, V2 maps to U2, V3 maps to U3, right, with this F. Okay, so what I'm talking about over here is, if you consider this one, right, it is a 1-to-1, but it is not surjective. So not surjective, right? And here we could ask the question that then what is the action of F inverse on V4 or V prime 4, right? That is this element, right? Because you can see that there is no function that is mapping to V4 over here. And in this case, if you look at this case, well, nothing much to say about this. It is a 1-to-1 surjective map, right? Okay, so well, it turns out that if A inverse exists, then it satisfies the linearity conditions as well, right? And furthermore, there is this commutativity between A and A inverse. So that is mathematically that A inverse is the same as A inverse A, right? Which is, of course, your identity. Well, now hold up over here for a bit and let's go back to our Pn polynomial and this differential d example, and consider this d on this nth degree polynomial, and we will introduce over here some sx. What this is it's the integral from 0 to t of some x that is a function of u, du, right? Okay, so we have just introduced this sx, and now we'll consider, for example, we'll take p4, right? And so yeah, here let's write down a function x is equal to t squared plus t. Now if I were to do this thing dsx, So that is, first take the integral that is defined like this of x, and then take the derivative with respect to t of x. So let me actually write this down. So what this means is derivative of this integral, that is u squared plus u du, right? And if I were to do this, what do I get? I get, well, of course my differential is outside. Inside I'll get u cube over 3 plus actually I'll have t cube because of this limit, right? Plus t square over 2. Now this thing is, if I take this derivative of this thing, right, it turns out that I get back t square plus t. So in so far I can say that ds is equal to e, and we are actually getting at somewhere from this, right? And you will quickly see what I'm trying to say over here. Perhaps right now you're wondering, what the hell am I doing, right? But there's something that I'm getting at, and at least I found it really interesting, right? Because it was, even for me, it was kind of counterintuitive to what I have been exposed to earlier. Well, let's continue. So far we have this thing, right? Okay, now moreover, what we could do is we could consider another example where we take derivative of this x first and then apply that integral operation that we defined like this, right? Okay, so let's go ahead and do that. So again, this thing just means that take the derivative of this function u squared plus u. Now if you take the derivative of u squared plus u, it ends up as 2u, right? And the derivative of u is 1, so like this. Now if I were to integrate this function 2u plus 1 with my limits from 0 to t as defined by this s, it gives me t squared plus t. So even right now, it turns out, or it appears so, that this s d is identity, right? So if I were to take a derivative and then integration, apply integration, I would get back the identity. Well, what I can do now is, now instead of changing this s and d, I will change my function, right? So let's consider some function x, that is t plus 1. With this, let's take this thing, that is ds of x. So I'll apply the integration on x and then take the derivative with respect to t. So if I do that, if I apply the integration on this, t integral of t would be t squared plus t squared over 2, and integration of this 1 would be t, right? Now let me take the derivative. I take the derivative, 2 comes down, and this thing becomes t plus 1. So, well, so far it appears though as this thing ds is identity, right? But what happens if I were to do sdx, right? Now if I take the differential or derivative of this function with respect to t, I end up with 1. Now if I were to take this s, now remember s on x was defined as the integral from 0 to t of x, that is a function of u du, right? Now let's take this we get 1, right? And now let's take the now let's apply s on this thing, right? I was getting confused because I forgot to write this s over here. Now, when we apply S on this 1 using this thing, what do I get? I simply get back a t, just one t. Where did this plus 1 go? Well, we did not recover it back. And so this tells you that SD finally it came out not to be equal to identity, which is, well, it's not a good thing for us, but well, that's how it works, right? That's what is true, and it doesn't matter what do we think, right? Okay, so from this, moreover, for x is equal to t4, right, plus some other terms, Sx belongs to V, right? Sorry, forgive me. Sx does not belongs to V, and why is that, right? That's a question. So let's answer that. Well, it's very simple, because since if I were to take this Sx, right, let's go ahead and take this integral for this t4, right? So using this definition, I will get t5 over 5 plus the integral of the other terms. What happened over here is this function is of the 5th order. But remember, we were working on P4, and so Sx does not belongs to P4. And P4 is our vector space over here. Now, the punchline over here is, let me get what I was trying to get at, is that this S or this integration thing is not a good inverse to D, right, to the differentiation thing. And that is simply because D or this differentiation does not have inverse, right, or does not have one, by one I just meant inverse. Actually, let me write inverse, right? That's what I was trying to get at. So again, you might have thought that the inverse of the derivative would then just be is just integration, right? But that's not true. It's not a good inverse. It works in some cases, as we had been seeing above, right? So it was working, and it even worked when we changed our function at one point, but then we saw that over here it did not work. So that's why I'm saying that it is not a good inverse to D, right? And that's what I was trying to get at. Hopefully you found it as interesting as I did when I first figured it out, right? So let's end this lecture here, right? In the next one, we will shift our attention to matrices and their inverses and so on. But let's end this over here, and let's summarize some of the things that we have covered so far. So first one being if A and B are invertible, right? So is then A times B, with A B inverse being equal to A inverse B inverse, right? And the other one, what we covered is if A is invertible and some alpha is not equal to 0, then alpha A inverse alpha A inverse is written this inverse is like this, then in this case we could write 1 over alpha times A inverse. Now note over here that this alpha is your scalar, so it's just a number, and that's why we could do this thing. We will just talk about this in a moment. Yeah, so the final point we could say is that if A is invertible, then so is its inverse, right? And what that means is that if I were to take the inverse of this inverse, I would end up back at A, right? Okay, so yeah, this was what we basically talked about in this video. And here, before I end this, I want to say something, and that is that do not and do not take this notation, that is A inverse, to interpret as it is a division by A, right? Do not do that. Of course, it is true for numbers, right? That is here when I talked about this thing over here, where alpha is just a scalar or a number. It is true, but it generally is not true. And so you will be making a mistake if you think of A inverse as it's just a division with A. Of course, the inverse of the multiplication over here is or this ordinary multiplication that you do, multiplication that is defined for numbers, you could say, in that case the inverse is the division. But this matrix multiplication or other complicated operators, right, it's not true. And so you would be making a mistake if you would develop the habit of thinking as this A inverse is just 1 over A, right? That's not generally true. Okay, so with this I will end this video over here, and on the continuing the series on mathematical methods, in the next video we will talk about matrices, right?